Um, Good afternoon, dear colleagues, ladies and gentlemen. It's my great pleasure and honor to be here today in such a colorful, hospitable, and bright country as India. And I am very grateful to organizing committee for setting up this meeting and for a kind invitation. So, while my topic of my talk in the program is nature-inspired nanobiohybrids for photo-energy conversion, since we are in India, I decided to spice up a little bit my talk, and a running title will be photo-energy conversion using nature's blueprints and building blocks. So let me quickly introduce what, if somebody does not know, students, for example, what Argonne National Lab is. It's one of oldest and biggest national lab in United States. It was established in 1946 for Enrique Fermi as a part of Manhattan Project. And the budget for 2016 was over $700 million. And fields of research include physical sciences, energy sciences, photon sciences, life sciences, computation and big data sciences, environmental sciences. Argonne is a home of more than almost 3,500 employees. Campus is almost 9 square kilometers, and it's located near Chicago and operated by University of Chicago. And we are proud to say that Argonne was a home of Nobel Prizes as Enrique Fermi, Maria Goeppert-Mayer, and Alexei Abrikosov, what is even more pleasant for me because of my Russian origin. And Argonne was also famous with herd of white deers. And actually they are freely walking through campus, and sometimes we can see them. And even more important, Argonne is well known for advanced photon source, brightest synchrotron, one of brightest synchrotrons in the world. Also, last years, Argonne became a national hub for battery research and solar energy research. Our division is called Center for Nanoscale Materials, is an unusual and special division in Argonne because it's one of 5 national nano centers funded by Department of Energy to help users from around the world, national users from academia, industry, government, to develop nanoscale materials. So in addition to development of own core program, we work with users, and it gives us more opportunity and flexibility in choosing research. That's why during today's presentation, so many things were mentioned about me in connection with nanobiotechnology for biomedical applications. However, our key effort is funded by Department of Energy and its development of energy materials and systems. So just if somebody is interested about coming virtually or in person to work with us at the Center for Nanoscale Materials, we work for free for users based on user proposal, and we have 3 calls a year. So you also can visit us at, maybe like us at Facebook. So my field of interest within the last 12 years, I believe, is nanobiofunctional materials or bio-nano interfaces. So we are getting inspired by biological phenomena as photosynthesis, vision, magnetic reception. We not only inspired by biological phenomena and biological events, we also use biological structures and combine them with synthetic or microfabricated inorganic particles and materials, assembly using chemistry or physical sorption, and to run function such as catalysis, imaging, sensing, manipulation, to bring these hybrids to outside world. And since today morning we heard a great introduction about main challenges of our days, and everyone has to try to contribute. Does not matter what your specialization is, as maybe as a member of an interdisciplinary team, you have to try to address such challenges as energy, water, food, and diseases. So I like that we live in an epoch of Anthropocene, and humans shape the world, including everything positive and negative of this. So this time includes or mediated by revolution technologies, status of energy resources. Actually, we are pretty much done with energy resources. They are exhausted, with a very strong environmental footprint of human activities. And also it actually affects culture. I include art and science. So what is our attitude and what we want to do to improve this situation, and how we are going to shape our future. So if we, one of main challenge is actually we are looking for more sustainable system and environmentally friendly system for energy future. I actually adopted with permission from Bloomberg Business this scheme. Is its projection of production of fossil fuels and clean energy till 2030, and it's in gigawatt. I believe I missed it. So if you look at 2013, you can see that if this is a milestone year, you can see that production of clean energy actually somehow became started dominating over fossil fuels, and that yellow bars, it's a proposal for development of solar fuels, and also hopefully by the middle by 30s, cost of solar energy is expected to drop tremendously, and I don't know how it will be true or not, but actually we all looking for this. Also for students and maybe younger scientists, younger researchers, we recently in spring 2015 published a big book by Springer Nature, and main contributors, main key players in the field of clean energy. Book is called From Molecules to Materials: Pathway to Artificial Photosynthesis. So if we are going back to nature inspiration and nature design, it's known that solar energy is used by living organisms, and the key or most known process of solar energy conversion is so-called photosynthesis. Photosynthetic apparatus is very complex. I'm not going to tell about all details. You can see from this image. Most important, It's chlorophyll dependent, cascading, multi-step electron transfer process that includes formation of photoinduced electrons and charge separation. However, there is another natural system, very sophisticated, very elegant, and very minimalistic. It's chlorophyll independent solar to chemical energy conversion system used by Archi. This is chlorophyll independent, few steps, no photo-induced electrons, no charge separation system. So I will return to latter system in a couple slides, and I would like to just quickly introduce that engineered photocatalysis or engineered photocatalytic splitting, also known as artificial photosynthesis, is pretty much bio-inspired and includes quite similar processes as charge separation and electron transfer. And water splitting reaction is thermodynamically it's an uphill reaction, and for overcoming this remarkable free Gibbs energy change, energy of photons can serve. So total reaction is 2 molecules water, light results in oxygen and protons and 4 electrons. This reaction includes 2 processes. First is oxidation of water, it's so-called oxidation half reaction. And the second one is reduction half reaction. Then result of this reaction is proton and electrons, which results in hydrogen. And despite of decades of tremendous efforts to develop both of these reactions, there are a lot of challenges to achieve perfect reaction. And usually groups are focusing on oxidation, like oxygen evolution or hydrogen evolution reactions, like us. So first report on successful water splitting using anti-semiconductor on single crystal electrode was reported by Fujishima sensei, Professor Fujishima, in 1972, I believe, yes. And this effect of water splitting on electrodes is known as Fujishima-Honda effect. A lot of citation is like kind of icon in this field. Then the system for photoelectrochemical water splitting includes titanium dioxide electrode and platinum electrode as a counter electrode. However, if someone imagine if we take these 2 electrodes and bring them very, very close to each other, like this, so we will result in nano hybrid particle, which is titanium dioxide and dot of platinum. And this system is called photoelectrochemical system, and this system is wireless and called photochemical water splitting system. We are mostly focusing on photochemical water splitting because of it's much easier, and hopefully we will have more practical impact. So since Fujishima and Honda reported upon photoelectrochemical water splitting under UV light, a lot of efforts were focused on transforming such system and improving this system for visible light photocatalysis, since UV light is only 4% of solar light reaching surface of our planet. And as dye synthesizers, they include a variety, like huge list of compounds or structures, including organic compounds, recent years quantum dots, even biomass. But focus of our group is introduction of assembly with biological structures. And here I just highlight some important or remarkable works published by other groups. And majority of these works are actually based on application of isolated photosystem from green plants with some nanostructures. Reaction conditions include a lot of cofactors, electron donors, and upon irradiation by usually people trying to do white light, here rates of hydrogen production. One of most interesting or more relevant to our work, the group from Great Britain by Armstrong is developing a different approach. They do not use photosystem. Instead, they use titanium dioxide nanoparticles as for production of electron-hole charge-separated system, dye-synthesized with ruthenium complex, and they utilize hydrogenase, which is known to be one of the most active biological system that able to reduce protons to hydrogen. However, this natural system is tremendously oxygen sensitive. So what we decided to do, we decided to use second natural system. I mean, it's alternative, evolutionary, distinct from photosynthesis, named bacteriorhodopsin proton pumps as a system to combine with semiconductor nanoparticles. So it's very interesting. It's only 26 kilodalton protein. It's a pore. There is membrane, cytoplasm, and it's extracellular space. And it's interesting, this proton pump is able to transfer protons through membrane, and that results in very remarkable electrochemical potential up to 250 millivolts. So if you look at this structure, this is membrane, and here's bacteriorhodopsin proton pump. Protons are pumped outside of host cell, actually utilized by ATP synthase for ATP synthesis. So this does not include any charge separation or actually formal photoelectrons. Cofactor of in bacteriorhodopsin is retinol, covalently linked through shift base to lysine residue, and upon absorption of photon of light, retinol goes through photoisomerization, pushing proton through the channel of amino acids, which protonate and deprotonate, and this is very simple, minimalistic approach. Important, hardly you can see it from your places, but if you see it, here is a sequence of bacteriorhodopsin, and whatever is green highlighted is aromatic amino acid. That's why if somebody who is familiar with electron transfer in natural systems, if you just don't know what it is, but look at this sequence, you would say, very possible this is electron transfer protein. But for some reasons, it's not in natural systems. So